Hey guys, good morning. Hope you guys are doing well and hopefully you survived yesterday's exam. I'll be getting those back to you in the next couple of days. Today we are starting chapter 3, which is definition of a derivative, which is one of the fundamental concepts in calculus. Now, the definition of a derivative, first of all, what is a derivative? All right, well, we're going to be describing exactly what that is and what it represents in this section. It is based upon the difference quotient. Okay, the difference quotient, and we've seen the difference quotient. All right, here's the one that we're, I think, most familiar with. This is the one that we deal with primarily, which is your f of x or a. They used a in this particular graphic. F of a plus h minus f of a all over h. Of course, that's when you have an x here, but there's another way to look at it, and that is in terms of a here. The difference quotient is f of x minus f of a all over x minus a. Okay, that should make sense. This ought to look a lot more like your regular slope formula, y2 minus y1 over x2 minus x1. Okay, so this is just another way to write the difference quotient. And earlier, in an earlier lesson, I showed you how we derived this from the slope formula. So, bottom line is, if we take this, or either one of them, okay, and we let this distance between these two x values go to 0, okay, then the slope of the secant line becomes the slope of the tangent line, because we can move that point, and we did this earlier, closer, 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 to where finally, if we move this and that distance becomes 0, then what you have here is a tangent line. Okay, a tangent line represents an instantaneous rate of change. And again, we talked about this earlier. So now let's just go down here and look at definitions. Okay, so definition of a derivative. Here are your two definitions using the two different formulas. The derivative of a function f at a point A is the limit of the difference quotient if it exists. Because remember, there are cases where the limit does not exist. Okay, so we have our limit of our difference quotient that we're used to dealing with as h approaches 0, that denominator, which is that distance, okay, approaches 0. Or we can use this one, the limit of this difference quotient, which is more based upon the regular slope formula, again, as x approaches a. Because a minus a here would of course be 0, which means your distance here is 0. Notice the notation. Given a function f of x, the derivative is denoted by f prime of x. Okay, f prime of x. And this is exactly how you would say it, f prime of x. Okay, this shows the relationship between the derivative and the original function. All right, now these two definitions, definition 1, definition 2, these are considered the limit definitions of a derivative. Okay, and I made a note of that up here, the formal limit definition of a derivative. Now, if you have had calculus before, then you are probably familiar with the power rule. All right, the power rule is a shortcut. Okay, if you are told you can use any method, then you can use the power rule, and we will be getting to that rule in the next section. However, if you are told to use the limit definition, then you will get no points for using the power rule, because again, it's a shortcut. And we'll see that a little bit later on. Okay, now what is a derivative? First of all, it's called derivative because it is derived from the original function. Okay, so you have your function, and then f prime is derived from it, and that's why it's called a derivative. But what does it represent? All right, well, the following are all interpretations for the limit of the difference quotient. All right, f of x plus h minus f of x all over h as h approaches 0. This is the primary one that I will use, although you may be asked to use both, or you may be given the option to use whichever one you prefer. Okay, so what does it represent? Well, it is the slope of the graph of y equal f of x at x equal, in this case, x naught. In other words, it is the slope of a tangent line, which is what the second point says, the slope of the tangent to the curve at that. Okay, uh, it gives you the rate of change of that point, and that actually is what step 3 says, or number 3. It is the rate of change of f of x with respect to x at that point. So in other words, the derivative represents how the function is changing at that precise moment. There are a lot of applications. This is one of the, like I said, one of the foundational concepts of calculus. So we're going to see a ton of uses for this. It's this derivative that one of the reasons that makes calculus such a useful math. So now, this is important. The following are conditions in which the derivative does not exist. Okay, and this all comes, except for the last one. I think the last one, I'll need to describe that one, but I think the first 3 kind of make sense if you consider where a limit would not exist. Okay, at a point of discontinuity. Okay, basically if the limit doesn't exist, then the derivative doesn't exist because the derivative is the limit. Okay, so a point of discontinuity, so that would be a hole in the graph, a jump in the graph, okay, an asymptote, etc. An oscillation, okay, that you'll see that with a sine or a cosine function. It's where it's just going back and forth, back and forth, back and forth to infinity and doesn't approach any number. Now, a point at which the tangent is vertical. Okay, so let's say you had a graph that looks something like this. Okay, and let's say you wanted to find the derivative at that x value. All right, well, if you did that, your tangent would be vertical. What is the slope of a vertical line? Do you guys remember that? Here's m for slope equals what? Infinity, or undefined. Why? Because remember, your slope is your rise over the run. How far is this rising? It's rising to infinity. Infinity over nothing here, over anything else is infinity. So that is implies does not exist. Okay, so a point at which the tangent is vertical is a point where the derivative does not exist. Now this next one may not make a whole lot of sense to you. Derivative does not exist at a corner or a sharp point. These are called, on a graph, a cusp. All right, so a good example of a cusp might be, how about an absolute value function? I'm gonna do a transformation over here. What if I, reflect it and it looks something like that? Well, right here, why would this not exist? Well, here's why it doesn't exist. Because at a sharp point, think of your tangent lines. Okay, at any other curve, okay, pick a point on a regular curve, and there should be just one tangent line that could be associated with that point. In other words, a line that would touch the graph at exactly one point. There's only one line. All right. How many tangent lines can we get on top of here? Well, here's one. Oh, here's one. Here's one. Here's one. Here. You get the idea? We could get an infinite number of tangent lines. Okay, an infinite number of tangent lines implies the derivative does not exist. Okay, that's the why. And this cusp, that is that point right here. That's what that's called. Okay, so here's our first example for evaluating derivatives. All right, so we want to determine the intervals on the following graph at which the derivative is positive. Well, recall that the derivative gives us the slope of a tangent line. So we are going to be looking for intervals at which the tangent slopes are positive. Okay, so let's take a look at the graph here then. So we're looking for the positive tangent lines, slopes that is. Okay, well from 1 to 3, is the slope positive? No, it's horizontal. The slope is 0. All right, how about from 3 to 5? Well, yes, it is positive. You could do positive. And of course, when you have a linear section, the tangent slopes and the average slope, your regular slope, are the same value. Okay, so clearly at every point here it's the exact same, and it is positive. So I'm going to say my first interval, and I have a couple intervals here, so I'm going to put them in a set, set notation here. My first interval is going to go from 3 and then it's going to end at 5, correct? So 3 comma 5, but what do I put around these? Would I put parentheses or would I put brackets? Well, hopefully if you noticed from 4 up above here that you would put parentheses because those are corners. And remember, corners, the derivative does not exist for the aforementioned reason. So therefore, note, whenever you are listing these intervals, always use parentheses. Okay, always use parentheses, even if it isn't a sharp corner. And we're going to talk about that a little bit later on in great detail. Okay, so what else? Well, where else are the tangent slopes positive? Well, it picks up here. Now, we didn't include this point because that's a cusp, but these are all positive slopes. Okay, I can come down here like this, right? These are all the slopes here are positive values. So it's starting at here at 5 and it's ending here at 7. Okay, so 5 to 7. And again, put parentheses. Now, I'm going to go ahead and talk about this here. There's no cusp here. So why did I not include 7? Because at this point, at the top of this curve, the tangent slope is what? M equals 0 for that slope. 0. Does 0 have a sign? No, it's the only number without a sign. Okay, so because that is 0, it gets infinitely close to it, but 0 itself is not a positive number, so therefore we always use parentheses. And I'm going to make a note here, not at x equals 3 or x equals 5, because they are cusps. Neither is it at x equals 7 because the slope of the tangent there equals 0. In other words, not positive. Okay, hopefully that makes sense. Okay, here's our first example where we actually get to do some math. All right, so here we're going to compute f prime of a in two ways using both limit definitions of the derivative. Here is our function, f of x equals x squared plus 9x, and our a value will equal to 9. So we're going to do this in two ways. Now, if you're told you can use any limit definition, you could use either one. If I tell you which definition to use, then you will need to use that one for full credit. But this is going to demonstrate to you that they will give you the same answer. One may be easier than another. You may prefer one over the other, but many times that is your call. So first of all, let's set it up. Okay, so I've gone ahead and just written out the formulas here. So here is one of our limit definitions. Here is our second limit definition. I just kind of divided it up to make it a little bit easier. Okay, so we know what a is. A equals 9. So that's my first step. This is going to be lim of f of 9 plus h minus f of 9 all over h as h approaches 0. Okay, so here I need to know what is f of 9. Okay, but first of all, I need to know what is f of a plus h. Well, what that means, and remember, and I know you guys have gone over this since pre-cal and algebra 2 and whatnot, but whenever you are plugging in a binomial, okay, into a function, all right, my advice is to put in parentheses first and then put that square and then fill in the parentheses. I see more errors done by not doing that step first than anything else. So I'm going to say this is the same. This is the equivalent of lim h approaches 0 f of 9 plus h. So everywhere there is an x, I'm going to put in 9 plus h, but put in, like I said, put in the parentheses squared plus 9. There's an x, so put in parentheses and then minus f of 9. What is f of 9? Okay, well, now I'm going to plug in 9 here. Well, 9 squared is 81 plus 9 times 9 is 81. 81 and 81, 8 and 8 is 16, 1 and 1 is 2, 162. See how you can do that in your head without even having to have a calculator? And now we're going to fill in the parentheses, all right, with the binomial 9 plus h, 9 plus h. Okay, and that's all over h. I promise, guys, if you do that step first, if you just take the 2 or 3 seconds it takes to do this, to put your parentheses and then your square and then everything parentheses and then fill in the binomial after you do all that. I guarantee you 9 times out of 10 you're going to get this problem right. It's when you don't do that, begin to make mistakes because people, forget, don't do everything to the power correctly. There's just a lot of room for error here. Okay, so now we're going to simplify it. Now we're just getting into some pure algebra here. 9 plus h quantity squared. So basically you want to FOIL it. 9 plus h times 9 plus h, FOIL it and simplify it. Now, I'm going to tell you that there is a shortcut. Okay, the shortcut whenever you are squaring a binomial, the shortcut is you square each term. 9 squared is 81. It's positive because it's squared, plus second term squared, h quantity squared. Both of these will always be positive, but there will always be a third term. That's where people make mistakes as well. To get the third term without having to go through the whole FOILing method, simply multiply these two together and double it, and it always works out. 9 times h is, of course, 9h. Doubled is 18h. It is positive, so plus 18h. Okay, so next, of course, we're going to distribute this 9 to both of these terms, so plus 81 plus 9h, and then minus 162, and of course this is all over h. Okay, there are two ways to determine, or to kind of checks, if you will, to verify that you are doing the difference quotient correctly. Okay, first check is right here. All right, when you simplify your binomial in your function, simplify everything, then every single term that does not have an h in it should cancel out, which means everything in the second part, this function right here, either f of x or f of 9, either way, should cancel out. Now, and it does. If we have 81 plus 81, that's 162. 162 minus 162, well, hey, they cancel out. Every single term left should have an h in it. Okay, now why is that important? Well, because we need to get rid of this. Obviously, as h approaches 0 in the denominator, that's going to make it undefined. But actually, it's not undefined, it's indeterminate because you would have 0 over 0, correct? So we need to factor out an h. This is why every single term in the numerator has to have an h in it, and it will always work out that it does. Okay, so if you get a term up here in the top that does not have an h in it, then stop, go back, and check your work. Somewhere in the arithmetic, something messed up. So we're going to factor out an h, cancel it, and then take the limit. So I factored out the h. Those cancel out. I'm left with this. There's nothing else to simplify. Now take the limit. So this equals what? 0 plus 18 plus 9, which is equal to 27. What that means is, this implies the slope of tangent line at a equals 9 is 27. Okay, that's what that implies. And we're going to use that. We're going to develop that out later on as well. All right, now let's look at the second part. Okay, when you are given an actual numeric value to evaluate, okay, you'll probably find the second limit definition to be easier. All right, so again, we're going to just plug this in. Okay, f of x minus f of a over x minus a. I don't need to plug in a binomial here. All I'm doing is plugging in wherever there's an a, or whenever there's whenever there's an x here, I'm just going to plug in 9. So I'm going to put in 9 here. That would be my f of a, correct? All right, so this is going to be lim as x approaches a, and a is 9, of f of x, which is my original function, x squared plus 9x minus f of a, and we already saw what that was. If you plug this in, we got that right here. That's 162 all over x minus a, and a, of course, is 9. Okay, so if you plug this in fact, you would get 0 over 0, all right, which is indeterminate. So that means we can simplify it. How can we simplify this? Conveniently, this is factorable. Now here is a hint, all right. Whenever you have a fraction like this, and you have a binomial, plain old binomial down here, and that's what's going to 0, chances are x minus 9 is one of the factors up here. All right, so just figure out 9 times what is 162. Well, as it happens, 9 times 18 is 162. So I'm going to say that implies lim. As x approaches 9, I'm going to open up my parentheses here. X minus 9 down here. And there's x minus 9. Okay, it's negative, so it has to be positive here. X plus 18. All right, because 9 times 18 is 162. And 18x minus 9x is, guess what? Positive 9x. That works. So then I can cancel this. Okay, and then I'm going to rewrite lim. X approaches 9 of simply x plus 18. And guess what? Take the limit. Equals 9 plus 18 equals 27. So yeah, that one was a little bit shorter, as you could tell. So I'm going to zoom this out so you can see the whole thing. And hopefully that makes a lot of sense to you. Okay, so we're going to now go on to the next page. Example 3 has 3 parts to it, parts A, B, and C, and those are the last problems of this video. All right, and basically it's doing what we did with the previous problem, but it is taking it one step further. We have one extra step involved. All right, so for the following 3 problems, use the limit definition to commute f prime of A, and then find the equation of the tangent line. Remember finding equations of lines? I mean, that goes back to what, Algebra 1, high school, right, freshman year? So, I mean, you guys been doing that for a long time. Hopefully you remember it. If not, that's why I'm going over it. All right, so it says limit definition. It does not tell me which one, so choose the easiest one. I think you probably noticed from the previous example that the second definition was a much more short, sweet, and to the point. So that's the one I'll be using, although either one will work. Okay, so here's the definition that I'll be using. Okay, I know that A is what? Well, what does A represent? A represents the x value of your coordinate. So A equals -4. F of A then would equal f of -4, which means we simply plug it in. But guess what, guys? If you're given an ordered pair, do you need to plug it in? No, you're given the output right here. We already know what it is. It's -51. Okay, so now we're just going to plug those in and just work the problem. Okay, so lim as x approaches -4, okay, of, here's my function, 3 minus 3x squared, because it's my original function. You don't really need parentheses around it, but because it's negative, I'm going to do that. Minus what? F of A. Well, what is f of A? It's -51. Be careful with these signs, guys. Those can certainly trip you up. Okay, all over x minus A. So x minus what? Minus a -4. Okay, so let's simplify that. And hopefully you saw that I forgot to put in this -3. I'm over here saying 3 minus 3x squared, but actually it's negative. So let me come back in here and put those in. Okay, so I went ahead and just distributed this and this right here, make those two positive. Now 51 minus 3 is 48, so plus 48 all over x plus 4. Okay, it's still becoming indeterminate, so I can factor out what here? I can factor out a -3. So lim x approaches -4 of, I'm going to factor out a -3, and that's going to give me x squared minus, because I'm bringing out a negative, that changes the sign, minus 16 all over x plus 4. Okay, hopefully you can see what to do now. And of course, I'm doing this in many individual steps. Obviously, you can combine some steps in this just arithmetic part, basically. Okay, so that would give me lim x approach -4. Remember, we have that variable is still appears here, so always rewrite lim because you haven't taken the limit yet. So -3 times x plus 4 times x minus 4 all over x minus 4 plus 4. My bad, sorry. Okay, and then of course now we can simplify this and get rid of that indeterminacy. Okay, that gives me lim of -3 times x minus 4, so that's -3x, and -3 times -4 is +12. As x approaches -4, Okay, and so now I'm just going to simply take the limit, and negative 3 times negative 4 is positive 12. 12 and 12 is 24, which is the, sorry about that, slope of the tangent line. Okay, there's my slope of the tangent. Now, like I said, I drew this problem out in great detail strictly for your benefit so that you could see all steps. Obviously, there's a lot of steps here that I could have combined, just FYI. You don't have to be that detailed. You can combine some steps when you're just working the algebra or the arithmetic part of it. Now, we are not done with this problem because it says, and then find the equation of the tangent. Okay, so to write the equation of the tangent line, we have the slope. Well, what do you need in order to write an equation of any line? You need slope, m, and a point. Well, we have both of those. M of the tangent equals 24, and my point is negative 4 comma negative 51. So now we want to write it as, remember our slope-intercept form? Remember that, guys? Y equals what? Mx plus b. Okay, that's what we want. Now, we can do it one of two ways. We can either use point slope. Remember point slope? Y minus y1 equals m times parentheses x minus x1. Remember that? You can do that, plug it in, and then solve for y. I usually just use this to solve for b, and then I've got my answer, and I'll show you what I mean. All right, I have 1, 2, 3 values. I have 1, 2, 3, 4 letters. Plug these 3 values in, solve for the remaining letter, and then I have everything I need. Okay, so that is my y value, which is negative 51, equals my m value of 24 times my x value of negative 4 plus b. Solve for b. Okay, what is b? That's negative what? This is going to be, okay, so that's going to be negative 51 equals negative 96 plus b. Add the 96 over, and you have b equals 45. So therefore, equation of tangent line is y equals m, which is 24x positive plus 45. Boom. All done. That's it. There's your answer. Hopefully that makes sense. Alrighty, these next two, actually last two problems, you'll do exactly the same as the previous one. Alright, they obviously take the algebra a step further because here you have a rational function with x in the denominator, and here you have a radical. But it works the same way. Again, use the limit definition, and I use that same one that I just used, but you could use either one. If you know the power rule, or in this case the chain rule as a matter of fact, or the quotient rule for that matter, if you know it, you can always use that to check your work. But again, if it calls for the limit definition, you get no credit, all right, for using the shortcuts. Guys, for you guys who have not had calculus before, you will be learning the shortcuts very soon. Okay, anyway, pause your video now and work these two problems, and then come back and check your work. Okay, well, here's the great reveal. Let's see. If you got this answer, then you would be correct. The final answer should be y equals negative x minus 1. Okay, so if you got that, good job. If not, then probably it was just an arithmetic or just an algebraic mistake. So now let's go over it. Okay, so here's our formula, and I've gone ahead and worked it out, and I'm just going to go step by step here. Okay, so we're going to put in our function f of x, which is 1 over x plus 3, okay, and then minus f of a. If we put in negative 2 here, 3 minus 2 is 1, so minus 1 all over x minus a, so that's x minus a negative 2, which is x plus 2. Now, we have a fraction within a fraction. There are a couple of ways to do this. One way to do this would be to get a common denominator here. But let me ask you something. Do you like fractions? You know, I have very few students who answer that with a yes. Most people do not. So my advice is get it out of fraction format. Don't keep it in fraction format. Let's get rid of this denominator right here. How do you do that? Well, you multiply top and bottom by that denominator and then distribute it. In other words, it would look like this. this is what I want to get rid of the fraction format. So if I multiply the top and the bottom of the main fraction, by that denominator and distribute it, then I've gotten rid of that fraction. Okay, and that makes it easier for most students to deal with. All right, so if I do that, all right, that's x plus 3 over itself, which is just 1, minus, and then 1 times x plus 3 right here. Look what I did here. I did not just go ahead and put in minus x plus 3 because invariably there's a mistake made. If you do that, you're just going to say minus x plus 3, but you have to distribute this negative. So if you did not get that answer, this might be what happened. You must distribute it. Okay? And then here's my second piece of advice. These two guys right here, leave these side by side. Okay, remember how when we were evaluating limits and you multiply top and bottom by the conjugate, and I said the part that's not the conjugate, don't distribute, leave them side by side? Very same reason, because it's this that's making it indeterminate, and we want that to cancel, so leave it like this. Okay, now simplify. That's negative x minus 3. Okay, again, forgetting that negative is going to change your answer. And if you get the wrong slope, then you got the completely wrong equation of the line. All right, so that gives me negative x minus 2. Now notice, to cancel it, this is x plus 2. So what could I do here? Well, how about factoring out a negative 1? I could do that. If I factor out a negative 1 here, then I'm basically changing both of these terms' signs. That becomes an x plus 2, and that is what's going to allow me to cancel this and get it out of indeterminate form. Which means now that gives me my limit of negative 1 over x plus 3 as x approaches negative 2. Take the limit by plugging it in, and you have negative 1 over 1, which is negative 1. That is your slope of the tangent line. Okay? Now that we have the slope of the tangent, then we can just simply come here, and I'll just go ahead and show you the rest of this as it is. All right, so our slope of the tangent is negative 1. Here's my ordered pair. Remember, you have to have a point. Now, we weren't given the point, but we did find out what the y value is, because right up here, that's f of a. If a is negative 2, if you plug it in, you have the y. So negative 2 comma 1 is my ordered pair. Plug it in here to slope intercept, or use your point slope and solve for y. Either way, you should have a... Okay, and here is our last problem, f of x equal the square root of 3x plus 5, where a equals 1. Okay, like before, I'm going to show you your answer, so hopefully you worked it out and got something. The math isn't all that hard with this. It's not the prettiest of answers. I'm going to forewarn you of that. It's not pretty, but you got it right. And by the way, I did rationalize the denominator here, but if you got this, then you did well. All right, here is the answer. Y equals 3 square root of 2 over 4x plus 7 root 2 over 4. All right, yes, it's not very pretty. And remember, I did say that I rationalized the denominator because there was a square root of 2 in it. So now let's go over how I got this, if that is not what you got. Okay, so I know that a equals negative 1, which means f of a equals f of negative 1. That's 5 minus 3 is 2, square root of 2. That's where that root 2 comes into play. Okay, so that means we're going to do the limit of f of x minus f of a all over x minus a. X minus a negative 1, of course, is x plus 1. All right, well, you've probably figured that because I have a binomial with radicals, hopefully you figured this, it's going to involve multiplying top and bottom by the conjugate, which are the exact same terms with opposite operation. Now that means that you're squaring the first term, which simply removes the radical, okay, which I'll go ahead and bring down here. You're squaring the first term, which just removes the radical. It's always going to be a negative because you'll always be multiplying opposite signs, regardless what order. And then square the first term removes that radical. And if you recall from before, you know, the part that are not conjugates, just leave them side by side, because this is what's making this go to 0, and this is what we need separated to cancel it out later. All right, so 5 minus 2, of course, is 3, and that comes down and looks like this. All right, again, we need to get rid of that x plus 1. Hopefully you can see what to do here. We're going to factor out a 3, and then we should be able to do just that. Okay, so here I'm going to cancel now my x plus 1's, and I'm going to write my simplified argument here, 3 over, this is square root of 3x plus 5 plus square root of 2. And now I'm going to actually take the limit as x approaches -1, and this is what it would give me if I did that. All right, so again, 5 minus 3 is 2, so that's root 2 plus root 2. I've got two of them. If you have one and you add one to it, you now have two of the root 2's. And like I said, I just rationalize this by multiplying top and bottom here by square root of 2. I don't need to multiply by this outer 2 here, because he's fine in the denominator. Now, if you did, you'll end up with a fraction that you can simplify. But that's okay. You know, we can do that. In any case, this is what I did, and I ended up here because root 2 times root 2 is root 2 squared, which is just 2, and 2 times 2 is 4. There's your slope of the tangent line. Okay, now we're going to come over here, and okay, here's your slope. Okay, 3 root 2 all over 4. Here's my ordered pair, and of course I already had that. I had that figured out from up here. Okay, right? And now I'm just going to plug it into y equal mx plus b. Y root 2 equal m times x -1 plus b. So that means this is going to be negative, which means if this is negative, to move it over, I'm going to add this over. So that would be b equals, okay, so you have 3 root 2 over 4 plus 4 root 2 over 4 equals, of course, 7 root 2 over 4. So there's my b value. Okay, and that would lead into my final answer, y equal mx plus b. No, I know it's not a pretty answer, but it is an exact answer. Now, why do I say it's exact? Because I didn't use a calculator and round root 2 to a decimal. All right, if you decimalize an irrational, then you've rounded it. It's an approximation. If you leave it in terms of radical, then it is exact. So that is your final answer. And that concludes this video. So hopefully this has made sense to you, and you'll see another video shortly. I hope you have a wonderful rest of your day. Take care, guys. We'll chat soon.